Africa is undergoing a dramatic transformation, a process so extraordinary that it's reshaping the continent itself. The Earth's crust beneath East Africa is breaking apart, tearing one of the largest landmasses on the planet into pieces. The Somali and Nubian tectonic plates are pulling away from each other, and a rift is expanding at an almost imperceptible rate. It's giving way to an ocean that could eventually change the world with it. In this video, we're going to bring you all the information about what's going on and whether there's a way we'd come out of this in one piece. The event that triggered global awareness was the 2005 Dabahu eruption. The seismic activity leading up to the 2005 Dabahu eruption was nothing short of extraordinary. In September of that year, the Dabahu area, situated along the Afar Depression in Ethiopia, began experiencing a cascade of earthquakes, over 130 recorded within a single week. These tremors were not minor events. They were powerful precursors to an unfolding geological phenomenon. Communities living in this remote area were both alarmed and bewildered by the intensity and frequency of the quakes, which caused the earth to rumble continuously. For residents who had no warning or context, it seemed as though the ground beneath their feet had turned volatile overnight. Each quake was a signal, a momentary burst of energy released as the Earth's crust pulled apart beneath the surface. Tectonic plates were tearing from one another, and magma was surging upward into the fissures created by their separation. The scientific community took notice as instruments recorded this rare alignment of seismic and tectonic events, and an unprecedented rifting process was set into motion. While small earthquakes are common in tectonically active zones, such a concentrated sequence pointed to a much larger event brewing underground. On September 26, 2005, the Dabahu volcano erupted, with magma pushing to the surface with violent force, ejecting ash, molten rock, and gases. While the eruption was not explosive by global standards, its sheer geological significance was unmatched. The event caused massive fissures, cracks that split the earth in ways visible to the naked eye. As a direct result of this activity, approximately 6,300 people were forced to flee their homes, seeking shelter as far away as possible from the unstable land. Entire families were displaced, and communities relying on agriculture were thrown into chaos as livestock was destroyed in significant numbers. Because of the sudden upheaval, the loss of livestock exacerbated the human impact of this disaster. The displaced communities faced immense challenges in the aftermath. Food insecurity became an immediate concern, as did access to clean water. Relief efforts struggled to reach some of the most affected areas, further showing the vulnerability of those living in the Afar Depression. Yet amid this human suffering, a global community of geologists and seismologists had their eyes fixed on what the region was revealing about Earth's inner workings. What made the 2005 Dabahu eruption more than just a regional disaster was the scale of geological transformation it triggered. In the days following the eruption, 37 miles of fissures opened up across the Earth's surface, stretching the landscape like a wound tearing deeper. These fissures weren't just shallow cracks. They extended dozens of feet deep, revealing molten rock and thermal activity. The Earth, in real time, was ripping itself apart, forming a rift that would continue to expand. The displacement of the ground was unbelievable, with sections moving several meters within mere days. Satellite imagery and ground observations showed dramatic shifts in terrain that seemed almost surreal to those witnessing it. For scientists, it was a vivid example of plate tectonics, the massive yet invisible forces of the Earth in action. The rifting was driven by the divergence of the Somali plate and the Nubian plate, two tectonic boundaries under incredible tension. As these plates drifted apart, the thin crust overlying them fractured, creating pathways for magma to rise to the surface. The Dabahu eruption became a rare opportunity to observe rifting on a human timescale. Unlike most tectonic processes that take millions of years, the activity at Dabahu unfolded over days, weeks, and months, allowing scientists to document and analyze each step of the process with unprecedented precision. GPS sensors and seismic equipment captured data showing that the 37 miles of fissures represented the initial stage of an ocean-forming rift. The Afar region was essentially laying the groundwork for the eventual creation of a new sea. These findings shed light not only on the tectonic processes governing the area but also on similar events that might have occurred millions of years ago during the splitting of ancient landmasses like Pangaea. This modern-day rifting provided a time-lapse view of Earth's evolutionary processes, offering critical insights into how landmasses fragment and oceans form. The Dabahu event illustrated that Africa's rifting wasn't theoretical or anecdotal but a vivid, undeniable fact. It demonstrated how the Somali and Nubian plates, previously considered locked, could actively tear apart with enough tectonic stress. Magma surging from below acted as a force multiplier, pushing the plates even further apart. For researchers, this alignment of forces was a textbook case study for understanding the mechanics of plate tectonics. While the 2005 Dabahu eruption marked a turning point in scientific awareness, it was just the beginning. Subsequent studies and ongoing tectonic activity revealed even more about how this rifting process would shape the continent and its people in the coming millennia. But what makes the Afar Depression so unique, and why does this region seem destined to transform Africa's geography? Understanding the East African Rift is key. The East African Rift is one of Earth's most striking geological features, stretching roughly 3,000 kilometers from the Afar Depression in Ethiopia down through Kenya, Tanzania, and into Mozambique. This vast rift marks the boundary between two tectonic plates, the Somali Plate drifting southeast and the Nubian Plate moving northwest. It isn't just a line on a map. The rift is a dynamic, evolving feature where the Earth's crust is actively breaking apart. The process began millions of years ago and continues to unfold before our eyes. Scientists often describe this zone as the most profound example of continental rifting on the planet. What makes the East African Rift particularly unique is that it's not just splitting the African continent in two, it's also creating entirely new geological structures, like valleys, furrows, and even future coastlines. Unlike the relatively slow tectonic shifts happening in many other parts of the world, this rift is active enough to be observed in human timeframes. The East African Rift owes its activity to one key driver: magma. Below the Earth's surface, magma wells up from the mantle, intruding into the rift and creating pressure that pushes the Somali and Nubian plates apart. As these plates drift away from one another, the crust in the rift zone becomes thinner and more fragile, forming fissures and fault lines. Magma intrusion is a core mechanism of this process, as molten rock finds its way into these fissures, cooling and hardening to form new crust. Over time, this creates a continuous cycle of destruction and renewal. Older crust is broken apart, while new crust is added in its place. The East African Rift is, in effect, a conveyor belt for new land formation, a phenomenon more commonly seen at mid-ocean ridges under the sea. But the forces shaping the East African Rift extend beyond magma. Gravity also plays a key role. As the rift expands, massive sections of the Earth's crust sink under their own weight, forming dramatic escarpments and deep valleys. These valleys often fill with water, as seen in the region's iconic lakes, like Lake Tanganyika and Lake Malawi, which trace the rift's trajectory. In total, this ongoing activity has already created one of the most geologically diverse landscapes on Earth, filled with volcanic activity, hot springs, and fertile soil. Over time, the forces pulling the Somali and Nubian plates apart will widen the rift to the point where water begins flooding the area, likely from the Red Sea and Indian Ocean. When this happens, Africa will split, and a new ocean basin will form between the eastern horn and the main body of the continent. This isn't mere speculation. It's an inevitability dictated by the principles of plate tectonics. Similar processes have happened before, most notably during the breakup of the supercontinent Pangaea around 180 million years ago. The Atlantic Ocean began to form when tectonic plates tore apart landmasses that would eventually become Africa and South America. Today's East African Rift is a smaller-scale version of that ancient process, but the end result will be no less dramatic. Though the creation of this ocean will take tens of millions of years, current activity shows we are witnessing its earliest stages. Some segments of the rift already dip below sea level, particularly in the Afar Depression, where magma-induced subsidence continues to lower the land. Satellite observations have shown that the rift is widening at an average rate of a few millimeters per year. Over geological timescales, this steady movement will result in the rift becoming unrecognizable from what it is today. When the ocean finally forms, it will not only change the physical geography of Africa, but will also reshape the global map. Future generations may recognize a continent split into two distinct regions with coastlines bracketing the newly formed ocean. The formation of a new ocean will dramatically alter the climate, ecosystems, and biodiversity of the region. Coastal areas will emerge where none previously existed, leading to new opportunities for marine habitats. However, this transformation will also pose significant challenges for human populations, particularly those reliant on the land for agriculture and livelihood. In places like the Afar Depression, where fertile valleys and lakes provide sustenance for communities, the flooding caused by ocean encroachment will likely displace thousands. Volcanic activity associated with the rift could also intensify as magma continues to rise and erupt, potentially threatening nearby populations. Moreover, the changing geology will influence local climates by affecting wind patterns, rainfall distribution, and access to freshwater resources. The East African Rift serves as a vivid example of tectonic forces reshaping our world. Yet the ongoing changes in this region are part of a larger, more intricate geological narrative, one that hinges on the unique characteristics of the Afar Depression, the epicenter of rifting activity, the engine behind the rift. At the heart of the East African Rift's dramatic transformation is the slow but relentless movement of Earth's tectonic plates. The Nubian Plate, which makes up most of the African continent, and the Somali Plate, representing its southeastern portion, are pulling away from each other at a rate of up to 2 inches per year. Though seemingly negligible on human timescales, this divergence accumulates over millions of years, resulting in massive structural changes to the Earth's crust. This movement is driven by convection currents deep within the mantle, where heat from Earth's core creates circulating currents of molten rock. These currents generate enough force to fracture the overlying crust, creating a divergent boundary between the Nubian and Somali plates. Unlike convergent boundaries where plates collide and create mountains, divergent boundaries like this one are zones of separation, tearing the surface apart to create new landscapes. The East African Rift is essentially a land version of what occurs along the world's mid-ocean ridges, like the Mid-Atlantic Ridge. Here, as the plates diverge, magma wells up from the mantle to fill the void. As it cools, this magma solidifies to form new crust. Over time, this cyclical process will expand the rift, eventually creating a full-fledged ocean basin. The mechanism is both simple and profound. As magma pushes upward, it weakens the lithosphere, causing it to fracture and thin. These fractures develop into fault lines and fissures, creating steep valleys and escarpments. In the East African Rift, the process is evident in regions like the Afar Depression, where active magma upwelling creates visible geological features, from basaltic plateaus to volcanic cones, a glimpse into Earth's past and future. This phenomenon of crustal creation is not unique to modern times. Around 180 million years ago, a similar divergent boundary formed between what are now the South American and African continents, leading to the formation of the Atlantic Ocean. The East African Rift offers a rare chance to observe this immense process occurring on land rather than beneath the ocean. The rift's progression is far from quiet. Seismic and volcanic activities are constant reminders of the forces at work beneath the surface. The tectonic stress generated by the diverging plates leads to frequent earthquakes, many of which are strong enough to alter the region's topography. For example, in the 2005 Dabo event, over 130 earthquakes struck within a week, providing a striking example of how these forces interact on a rapid timescale. Volcanic activity is equally significant. The East African Rift hosts some of the world's most active volcanoes, including Erta Ale in Ethiopia and Ol Doinyo Lingai in Tanzania. These eruptions not only release vast amounts of magma but also reshape the surrounding landscape by depositing new layers of volcanic rock. Magma chambers beneath these volcanoes also play a critical role in weakening the crust, accelerating the rifting process. Geothermal features and future landscapes are another hallmark of the region. The formation of geothermal features like hot springs and fumaroles, where heated groundwater escapes to the surface, signifies the proximity of magma to the Earth's crust. Over time, the combined effects of plate divergence, magma upwelling, and seismic activity will lead to the formation of a new ocean basin. As the Somali Plate continues to drift away from the Nubian Plate, the rift will expand and eventually allow seawater from the Red Sea and the Indian Ocean to flood the region. Once the process is complete, the rift will resemble modern-day tectonic boundaries like the Red Sea or the Gulf of California. The Afar Depression, a low-lying area near the rift's northern end, offers a glimpse into this future. Parts of the depression already sit below sea level, and cracks in the crust occasionally allow groundwater and magma to interact, creating boiling mud lakes and temporary lava lakes. Eventually, these features will give way to permanent water bodies, marking the birth of a new ocean. The stages of ocean formation are a step-by-step process that transforms landlocked terrain into a vast body of water. This transformation is governed by tectonic forces driving the Somali Plate and Nubian Plate apart. The progression unfolds in 3 distinct stages. First, the rift transitions into a valley. This stage begins with the formation of fault lines and fissures as tectonic plates diverge. Magma wells up through the thinning crust, creating volcanic activity and earthquakes that reshape the landscape. Over time, these processes widen and deepen the rift valley, forming elongated depressions bounded by steep cliffs. Next, the valley evolves into a gulf. As the rift deepens, parts of it may dip below sea level. Water from adjacent oceans or seas like the Red Sea or Indian Ocean begins to seep in, forming isolated gulfs or narrow waterways. This stage is exemplified by regions in the Afar Depression, which are already below sea level and demonstrate early signs of water intrusion. Finally, the Gulf develops into an ocean basin. Over millions of years, continued divergence widens the Gulf into an expansive ocean basin. Magma continuously rises to form new seafloor, and tectonic activity keeps the boundary active, further expanding the ocean. At this point, the rift's geology will resemble that of established mid-ocean ridges. The projected timeline and impact of this transformation provide a rare chance to witness the ongoing geological processes that will eventually reshape the geography of Africa and the surrounding regions. The early stages of oceanic creation, while seemingly frozen on human timescales, hold immense geological significance. Scientists estimate that a fully formed ocean will emerge in roughly 5 to 10 million years. Current rifting rates, approximately 2 inches per year, drive this timeline, though geological disruptions could accelerate or delay the progression. As the rift progresses into an ocean, the separation of the Somali Plate from the African continent will create a striking geographical shift. A new island, comprising parts of Ethiopia, Somalia, and Djibouti, will form along the rift's eastern boundary. This landmass will be surrounded by the waters of the newly formed ocean, similar to how Madagascar split from Africa millions of years ago. Coastal zones will likely experience cooler, wetter climates, while inland regions could face aridification. Over time, these changes could reshape agricultural patterns and ecosystems. Geological history shows that processes like those underway in East Africa have reshaped the planet, driven biodiversity, and transformed climate systems. By studying events like the formation of the Red Sea and Atlantic Ocean, we can better understand what lies ahead for this emerging ocean and the region it will forever change. That sounds really terrifying, but at the same time, we have technology right now that can help us take a closer look into this whole thing step by step. Modern technology plays a critical role in understanding and monitoring the East African rift's progression. By combining satellite observations, seismic instruments, and advanced models, scientists can not only track current changes but also project the rift's long-term transformation. The rift's evolution has been meticulously tracked through cutting-edge satellite imaging and GPS technology. These tools enable real-time monitoring of ground deformation and tectonic shifts, offering unprecedented detail into the ongoing processes beneath East Africa. Satellite interferometry compares radar images over time to identify subtle ground movements in the East African rift. INSAR has detected areas of ground subsidence, uplift, and fissuring associated with magma movement and tectonic activity. Fixed GPS stations across East Africa measure tectonic plate divergence, detecting movements as small as a few millimeters. These measurements confirm the Somali and Nubian plates' steady separation at rates of up to 2 inches per year. Satellites have captured images of magma rising beneath the rift, contributing to surface deformation and seismic activity. By analyzing thermal imaging and ground changes, scientists can pinpoint regions where new crust is being created, particularly around active volcanic areas like Erta Ale. Seismic networks deployed across the rift region have already provided invaluable data on subterranean activity. Arrays of seismometers identify the frequency, location, and magnitude of earthquakes along the rift. Clusters of low-magnitude tremors often indicate magma movement, while larger quakes signal significant shifts in tectonic plates. By analyzing seismic waves, geologists can determine the depth of magma chambers and fault zones. This has revealed that volcanic systems within the rift are fed by magma intrusions extending several miles below the surface. These seismic insights not only help forecast eruptions but also contribute to understanding the complex interplay between tectonic forces and volcanic activity. Predicting the future landscape of the East African rift relies on advanced geological models that incorporate real-time data, like dynamic simulations of rift expansion. Models simulate the continuous divergence of tectonic plates, predicting the eventual formation of a new ocean basin. This includes mapping the timeline for the rift's transition from a continental valley to a fully submerged ocean. These projections show us how areas like the Afar Triangle may eventually form an island separated from the African mainland by seawater. By integrating data from ground deformation and seismic studies, scientists model the interactions between magma and crustal structures. These simulations offer predictions on where new volcanic systems may emerge or how crustal thinning will advance. Innovations in remote sensing, AI-driven data analysis, and autonomous field instruments are expanding the scope of rift monitoring. AI algorithms can analyze seismic and satellite data faster and with greater accuracy, identifying patterns human observers might miss. Drones and rovers can be deployed in dangerous terrains to capture high-resolution images and collect ground samples, providing critical data from the rift's most inaccessible zones. As technology continues to evolve, so too will our ability to monitor and predict the East African rift's changes. The integration of these tools has not only provided detailed insights into the rift's current state but also set the stage for anticipating its future. With these technological advances, humanity is better equipped to understand what's coming and prepare for it. The people living in the immediate vicinity of the East African rift, particularly in the Afar region, have developed remarkable strategies to survive and adapt in the face of ongoing geological changes. These communities have lived through some of the planet's most active tectonic regions, and their ways of life have shaped up in response to the intense volcanic and seismic activity they encounter daily. Because of the scarcity of freshwater resources, locals have cleverly utilized geothermal energy in the Afar Depression. Volcanic steam vents provide a constant source of heat, and indigenous communities have adapted by collecting the steam rising from these vents and condensing it into drinkable water. By harnessing these naturally occurring sources of geothermal heat, people create simple yet effective systems for water purification and collection. This practice allows the Afar people to survive in an otherwise arid environment, making use of resources that are often regarded as dangerous or unusable. Another remarkable survival technique involves the use of obsidian, a type of volcanic glass that is widely available in the region. The Afar people have a unique method for testing obsidian to ensure that it is not contaminated by harmful volcanic gases. Before using obsidian to craft tools and weapons, locals test the mineral against natural benchmarks to determine whether volcanic activity has altered its properties. This traditional practice ensures that the obsidian is both safe and effective for everyday use, a crucial strategy in a region where volcanic eruptions are frequent. While living near active volcanoes and seismic zones presents serious risks, the rich mineral resources found in the region provide significant economic opportunities. The East African Rift is home to a wealth of resources, including geothermal energy, volcanic ash, and valuable minerals like gold, copper, and salt. In Ethiopia, geothermal fields are already being tapped as part of a growing industry that harnesses the power of the rift's underground heat. As geothermal power plants increase in number, they could provide clean, renewable energy not only to the local population but also on a much larger scale, offering a model for sustainable energy production in other parts of the world. The extraction of minerals from the Rift region also provides economic stability, especially in countries like Ethiopia and Kenya, which benefit from mineral exports. In addition, the fertile volcanic soils, which are ideal for agriculture, continue to attract farmers, both local and international, seeking to exploit the area's unique ecological advantages. As the East African Rift slowly transforms into an ocean, it is expected to dramatically reshape the environmental landscape, not only in East Africa but also potentially influencing global ecosystems. The formation of a new ocean could alter atmospheric circulation patterns, leading to changes in rainfall and weather across the continent. Areas that are currently arid or semi-arid may receive more moisture as ocean currents redistribute water, making these regions more suitable for agriculture and boosting overall biodiversity. On the flip side, areas already receiving substantial rainfall might experience shifts in climate that could lead to drier conditions, particularly in areas located further inland. The creation of such a large body of water could trigger a significant redistribution of heat and moisture, causing widespread changes in regional and global climates. This phenomenon would have profound impacts on the ecosystems surrounding the rift, as new environmental niches emerge, creating opportunities for species to adapt, migrate, or even become extinct. But the Earth has done it before and it can do it again. What do you think? Leave your thoughts in the comments below, and if you like this video, don't forget to subscribe to our channel. See you in the next one.